at the end. Wait. It's kind of the little investigation we did at the end of class on Friday. That big mathematical proofs. Your side. at least. Okay. And then when you do this, what do you get? 0. So it just kind of goes away. Okay. So anyway. A chain rule with the derivative then. And so I have been substituted in there, but then when I do that, I also have to take the derivative of whatever I multiply that on the end, right? So what do I have to still have multiplied onto this thing then? This time? That's right. You guys remember that one? You can switch the lower and upper limits, but you have to make the whole thing negative to do that. Um, How is this one different from all the other ones we've been doing? Well, that's true, but that's not what. What? Yeah, both limits have x on them. Okay, so we can't exactly apply that formula. We're supposed to go from a to x. But see, it goes from x. You know, 0. You can chunk it. Areas. Modify these as needed to get it done. Yeah. Okay, so here let's take a look at part 2 of the Fundamental Theorem of Calculus. And this part you guys have kind of sort of already investigated as well, but it's good to get it just written out in words here for you. So it says, if f is continuous at every point of the closed interval AB, and I gotta back this up just a little bit so that the camera can actually see it, which means I'm going to have to now adjust that. Okay, so if f is continuous at every point in AB, and if big F is any antiderivative of f, bless you, then the integral from a to b of f of x dx is equal to big F of b minus big F of a. And that was that. I had you guys do that extra little reading at the end of the last section, and basically that's what that was getting at, was this idea that kind of stemmed from that investigation you guys looked at. So this is that connection between derivatives and integrals, right? So an antiderivative is a way to calculate an integral then. And moreover, the antiderivative of the upper limit minus the antiderivative of the lower limit will get you the value of that area, whatever it is. Notice how it says any antiderivative of f. Okay? There's more than one antiderivative for any function. Why is that? We've talked about that before. When we do an antiderivative, what do you always have to stick at the end? Plus c, right? So there's an infinite number of constants that could be at the end of it. Okay? But think about how this formula works, and you'll see it doesn't matter, whatever that constant is. Okay? If I'm doing f of b minus f of a, when I plug a number into a function and there's a constant at the end, I'm not really plugging anything into that constant, or that constant isn't really changing, right? So f of b is going to have some function with stuff plugged in, and then the constant I'm going to subtract that same exact thing with a bunch of stuff plugged in, and that same constant. Well, what's going to happen to those two constants? They'll cancel. You're subtracting them, right? And they're exactly the same thing. They'll just go away. So you can put whatever the heck constant you want. It's not going to make any difference, because when you go through and do that subtraction, they're going to cancel each other out no matter what anyway. So typically what's done is when you do this, you do an antiderivative where the constant is just 0, because it doesn't matter and it makes it easier. Okay? So, then, so how about we calculate the integral? Let's go, I don't know, 1 to 3 of (2x minus x squared dx), and see if we can follow this antiderivative idea for this. Okay, so first thing that we have to do is figure out what is the antiderivative of 2x minus x squared. Okay, and we can just go term by term like we've done in the past. Okay, so what is the antiderivative of 2x? X squared, good. And what is the antiderivative of negative x squared? Mm-hmm. And what I always do is, especially with polynomial ones, is try to do it backwards then. Once you have your antiderivative, think about taking the derivative of that, and does that bring you back to where you started or not, to kind of check. So derivative of x squared, 2x. Derivative of 1/3 x to the third, bring the 3 down, so it'll be just x squared. Okay, yep, it works. And then put this little bar on the end of it. This is probably something new for you guys here. That's called an evaluation bar. And basically what that's saying is it's kind of like a way of rewriting those limits on there, but it just means evaluate this starting at 1 and going to 3. But if we follow this pattern here, I'm actually putting the 3 in first and then putting the 1 in and doing a subtraction. So here's that process then. So I've got to plug in the 3, so it's going to be 3 squared minus 1/3 times 3 cubed. So it's whatever I get from that, that's plugging in the 3, minus, plugging in a 1, 1 squared minus 1/3, 1 to the 3rd, like that. Okay, so I plugged in my b, which was 3, plugged in my a, which was 1, and I get each of these individually, then subtract them, and that's going to be the value of that integral then. So let's see, so 3 squared, that's 9, minus 1/3, 3 to the 3rd. Well, this 1/3 will cancel one of those 3's. So that'll be 9. So this is actually 9 minus 9, 0. And then over here we've got 1 minus 1/3. So that's 2/3. So this should be negative 2/3. Okay, let's use our calculator real quick, give you a chance to on the how you do an integral on your calculator. And let's double check it, see if we get the same answer. Okay? Alright, so remember we go to math and then all the way down to fn int. And it needs 4 things. It needs the function, it needs x, it needs the upper limit, and the lower limit. Or actually, it goes lower than upper, sorry. So, 2x minus x squared. Our variable is x. Lower limit is 1, upper limit is 3. So it should look like that once you got everything in. Hit enter, and we should be seeing negative 2/3. I hope. Oh, good. All right, so we verified it. Yep, that's correct. Doing it that way. So, derivatives, we're going to spend a lot of time in later chapters talking about how to come up with antiderivatives. If we're dealing with polynomials, we can pretty much handle that right now. Okay? And there are certain other ones, like some of the trig, cosine, and sine, that we can do some antiderivative work with. Certain other ones, if they give you a formula like secant squared, we know actually goes back to tangent. Some of the logs and exponential stuff, we can kind of play around with some of those too a little bit because we know those formulas. But as soon as I start to make equations that are like combinations of those or a little more complex, we don't have like a chain rule for antiderivatives like we do derivatives. So we can't get through some of those hoops necessarily like we used to with derivatives. And so we're going to spend a lot of time talking about techniques of integration down the road, about how do we get through some of these other equations and get integrals for them and that sort of thing. In the groundwork, though, so we're not going to get anything more complex. So, now doing it though, at least with certain equations, we're going to revisit this idea of total area versus signed area. Same. Now we're going to see what can we do by hand. Now that we have this technique for doing integration by hand, if we wanted total area, let's say, how could we do it? Okay, doing an integral straight ahead like this. Okay, just going from the lower limit to the upper limit, using that fundamental and getting an answer. Is that total area or signed area? That's always signed area. Okay. The total area, I need to know where this function is above the x-axis and where is it below the x-axis. Okay? So, I'm going to take a function that I know definitely crosses the x-axis. And we're going to use that to do a little bit of an investigation here as far as how we can get that total area. So let's say we've got the integral. Oh, we'll go from maybe -2 to 5. And we'll do x cubed minus 5x plus, 5 squared plus 6x. Okay, that one we can handle. So, like I said, we need to know where is this function above the x-axis, where is it below the x-axis, before we even start to use the fundamental theorem and evaluate this integral. Okay? Because there are certain portions that are going to be positive, certain portions that are going to be negative, and if I do this integral straight ahead like this, those positive and negative pieces are going to start to cancel each other out, right, with that signed area, and I'm not going to know exactly how much was below and how much was above because there's going to be all this kind of like mysterious cancellation that happens that I'm not actually seeing, that it's just going to be gone. So what do I need to do then to start this thing off? You did a bit of this in pre-calc. I want to know where is it above the x-axis, where is it below. So what ultimately am I looking for then? What tells you when a function is above and below the x-axis? Okay, and what separates positive and negative? What's in between all of those intervals? Zeros, yeah, right? If it's going to be above, then below, then above, that sort of thing. I need to know where those zeros are, right? Because then I can split up. Oh, here's like the part, here's a part below, but it's these guys that are giving me those intervals, right? So I need to do that first, okay? So I need to take a look at this function before I even do an antiderivative, anything else. What are its zeros? How are zeros? Factor it, right? Factor it, set it equal to 0, and then we got it. So let's do minus 5 squared plus 6x equals 0. Let's see if we can solve that. So what would be a good first step in that factoring process then? Yep, you can take out an x on this one. All right, can I go any further with it? X squared minus 5x plus 6? Yep. What does that factor to? You got it. Okay, so where are my zeros? X equals 0, x equals 2, x equals 3. Okay, so what that means is I need to not just take one integral, I need to take several that are broken apart by these zeros. Okay, so if I look at my limits of integration right now, I want -2 to 5. Okay, my zero that I run into is 0. So the first chunk I want to look at then is -2 just to 0. Get that one. And then the next chunk would be 0 to 2. Get that one. And then 2 to 3. Get that one. And then 3 up to my upper limit of 5. And get that. These are giving you those places you need to chunk this thing out. Okay, where we know it's going to be cut apart into these positive and negative chunks as we go. So several calculations to get this thing taken care of by hand then. Okay, so if we go -2 to 0 of x cubed minus 5x squared plus 6x dx, see what we get for that. So the antiderivative, 1/4 x to the 4th minus 5/3 x to the 3rd plus 3x squared, and that's it, and then evaluated from -2 up to 0. Now for this kind of stuff, I'll let you guys use, like with your last quiz, I'll let you use a little scientific calculator, okay? I'll let you do that. So if you want to use your calculator to plug some of these numbers in, not a big deal, okay? So we need to plug 0 and plug in the -2. Well, one of those I'm pretty sure you can do in your head. What is f of 0 in this case? 0. Okay. So we've got 0 minus whatever we get when we plug in the -2. So I'm going to do that on my calculator. 0.25 -2 to the 4th minus 5/3 -2 to the 3rd plus 3 times -2 squared. Wow, okay. That's huge. Okay, I got 40,632.3 repeating. Did we not get that? I got some weird. Oops. Hold on. No, that's not right. Yeah, where I meant to put a parenthesis, I put a 9. That makes a big difference. That sure would. 29 1/3. Woo, that's a lot nicer. Difference one button can make, right? 0.3 repeating. Okay, so we're getting an answer that is -29.3 repeating then. So was this interval above or below the x-axis then? But below, right? Because it's -29.3. Okay. Now, total area, do we care if it's above or below? Nope. So we would technically be using a positive 29.3 to describe that total area portion there. Okay. So when we go back to the end, I'm not going to keep the negative on that thing anymore. But that just shows you that that portion was underneath. With my next one, I said I had to go 0 to 2, right? Because my zeros, that's my next chunk. So 0 to 2 thing. So same antiderivative, that's nice. Don't have to redo that. Except now I'm going to evaluate it from 0 to 2. So if I put in a 2, 1/4 times 2 to the 4th minus 5/3 2 to the 3rd plus 3 times 2 squared. 2 2/3 it looks like. Or 2.6 repeating. And then if I put, obviously I get a 0, so 2.6 bar would be the area of that chunk. So that one, switches from being below the x-axis to above the x-axis, so this one just a tiny bit above, though. What's my next interval, then, that I got to do? What to what? 2 to 3, okay. So again, same antiderivative. So now it's from 2 to 3. Okay, after 2, I know what I get from that. So after I plug in the 3, I can just steal my answer from the second one. So 1/4, 3 to the 4th minus 5/3, 3 to the 3rd. Plus 3 times 3 squared. So that's 2.25. But then I got to subtract plus 2, which we found was 2.6 repeating. All right. And that gives us looks like negative 0. It's about negative 0.417, looks like. All right, and then we got one last chunk. I'm kind of running out of room, so I'm going to squeeze it up here. We still got to go 3 to 5, right? Our last little chunk. The same antiderivative. Except now I'm going 3 to 5. Okay, so what do we get from that one? So plug it in a minus 5/3 times 5 to the third plus 3 times 5 squared. So 2.92 looks like. Except minus what we get when we plug in the 3, which was 2.25. So it looks like 20.6 repeating now. So here's what we came up with, the results of each of these. So our first interval, we had this, negative 29.3. Second interval, we came out with 2.6. Third interval, negative 0.417. Fourth interval, 20.6. The total area, okay? Or all the negatives, right? I just want how much area, how much area, how much area, how much area of each one of those. And so every number's up except get rid of the negative signs. And that should be what we've got. And we can round off a little bit too, it's fine. So I'm getting about 59 for my total area. Oh, I'm sorry, 52.9. My bad. Okay, so that, again, that's the total area, not the signed area. If I the signed area, I could have done this, I guess, and added up all of these with the negatives included, right? But it would be the easier way to do this if I really wanted signed area. Because I've had students do this in the past, and it made them very mad. Just do the antiderivative using negative 2 and 5, because your negative stuff's going to cancel itself out in the middle of that anyway. You don't need to chunk it unless you need total area, okay? Total area, we have to be able to know where it switches, and then break it into those little pieces so we get all that negative area, all that positive area, all that negative area, so we know exactly how much of each little chunk we have, and then we can just add them all up as if they were all positive and get that. So, does that make sense? How I have to do that? Some functions are easier than others, obviously, but that's the idea. So total area, chunk it. Signed area, just do the regular antiderivative and go. It's fine. Okay? So, some antiderivatives. The last thing we're going to do. So, let h of x equal the integral a to x of f of t dt. All right. So h is like the antiderivative of f. Okay, or the h is the integral of f. Notice how this is h of f limit on that integral. And this is f of t dt. We're going to analyze this graph of x. Okay? Alright, so x, y, and then this is x. And this is at 1. Let's see, that peaks out at 3. This is at 4. That comes down at 6. And then this is at 8. Okay. And so I'm going to ask you some questions about h. And you need to use the graph of f to do that, to answer those questions about h. Right, okay. So let's see. So how about h of 1? We'll start off with an easier one here. So h of 1. And my bad. This was not supposed to be a. This is supposed to be 1. We don't know that. We can't really do this. H of 1. Okay. If you look at the original function, or that I gave you up there, h of 1. If I make x 1, 0, right? Because what that implies is h of 1 is equal to the integral from 1 to 1 of f of t dt, right? And any integral where the bottom limit and the upper limit are exactly the same thing gives you 0. Okay? Now, it's 0 because of that. It's not 0 because of this. Does that make sense? Because h, this is not h. What is this? This curve f. It's not h, right? So h 0, or h of 1, is talking about the integral. F of 1 would be talking about the y value on the curve. Okay? So keep that in mind. Nope. It's f of x. Okay. The t, we call that a dummy variable. The only reason that that's a t is because this variable and that variable can't be the same because they're talking about two different things. However, when you look at the graph, this has x because this h of x is referring to a limit of 1, some number we don't know. But that number we don't know is along this axis, right? So it's from 1 up to some x. What's the area? So if I did like h of 6, it would be the integral from here to here. And the answer of h of 6 would be the area under here up to 6. Okay? Dependent upon an x, right? So this has an x-axis then to make that work. That always throws people off. The only reason it's a t is because it has this, because it's talking about two different types of things there. Okay? you can still call this f of x and it works. Okay? So that's kind of the crucial thing we need to be thinking about as we go through this is an area. The answer to h of x is an area under this particular curve. Now, I'll tell you of area under it at that position. So my question is h of 0 positive or negative? So if we look at h of 0 is the area. However, we're starting at 1, right? So it would be the integral from 1 to 0. So from 1 to 0. Is that got to be positive or negative? Technically negative. Okay? The area, if I 0 to 1, would that be positive or negative? If my limit was 0 and my upper limit was 1, that area is positive, right? But I have it switched, right? I'm starting at 1, and I'm adding this one. H of 0 would be 1 this way. So going in that actually makes it negative. So it's yes. Exactly. Yeah. So because if this was my lower limit and this was my upper limit, that would make it would make a negative negative then. Yep. E says h of x has h of x is area. Okay? I'm not looking for where f has a maximum. I'm looking for where h is maximized. Okay? So where, as you sweep left to right, starting at 1, as you sweep left to right, where does it have a maximum? Where is the area the most? And we're talking signed area again, right? So where is the signed area as big as it could be?
1 to 4.
Once you get to 4. Okay? Yeah. So the value of x has 4. Now, with f of x, this is a 0, right? But take a look. This is all positive area up here, right? So as we move over, once we get to 4, that's the positive area we can get, right? And then as soon as we get past 4, then we've got a negative signed area that's going to start to cancel out that positive area we had already created, right? So 4 has to be the maximum for h. So we'll say x equals 4 because this is the most positive area. All right, I guess I'll jump over here to do D. So the next one, h of x has a minimum. So what do you think? So think of it this way, if we were to stop at a certain point, where would we have the most negative area? You have to start at 1. Mm-hmm. 8. Okay, so we'll see that. Now the way this was drawn, it's pretty obvious that the area underneath was more than the area above. Okay. This is where you hit your maximum. As soon as you get past 4, now that negative area that's going to start to cancel off that positive area. And eventually we're going to get to some point where the negative area equals that positive area, but then we keep getting more and more negative area until we get to 8, and then we're back up to no more negative area, and we've maxed how much of this we have, and we've canceled the most of this that we can. So, yeah, it's got to be the 8. Okay. Mm-hmm. Yeah, technically. So if we were to continue to move on there, the way that it's drawn, it appears as though it's going to break through the x-axis and go back above, right? So then you'd be adding on more area, right? Well, if you had another interval up there, then you'd have to kind of know how much. Out to like, I don't know, 10 or 12 or something else, and we had it continue to go up and get bigger. Then we could say that x equals 4 is a relative maximum. We know that it's going to be the most kind of in the area right there, but then it's going to start to go negative. For an absolute, we wouldn't really know unless we knew exactly how much, in each little piece, because then we could compare, okay, now start to cancel off some of this negative area that we had in excess, right? And then eventually we might equal out how much we had here and maybe even get bigger, and so we'd have to kind of compare that a little bit. But, yeah. For right now, assume all of these are just mins and maxes and that sort of thing. Yeah. So, the next one, of all points of inflection. It's a good one. Okay. What's a point of inflection? When the concavity changes. Okay. If the function is a nice, smooth, differentiable, continuous function, what do we know about derivatives that has to happen at a point of inflection then? Second derivative can equal 0 there. Okay. So, we're talking about x. Okay. So, h of x is the integral of f of x. Okay. We need to get through 2 derivatives. If I do just one derivative on h of x, what happens to this integral? What's the derivative of an integral? What happens? What did part of the fundamental theorem of calculus tell us? Those two things do what? They cancel out, right? So if I do a derivative of the integral, the first derivative of h is f. Does that make sense? The first derivative of h is f. What is the second derivative of h? The derivative of f, right? The second derivative of h is the first derivative of f. Okay? So, h double prime x could equal 0 there then. So what that implies then is that it is where the first derivative of f equals 0. Which we can find on a graph, right? By looking at its shape. So where does f prime equal 0? 1, 3, and 6. So 1, 3, and 6 are those places where the first derivative of f is equal to 0, so therefore it is where the second derivative of h is equal to 0. So, yeah, that'd be it, those three. X equals 1, x equals 3, x equals 6. Okay, so does this kind of thinking make sense to you guys? It can be a little bit tricky. You're thinking about the area as a function to do this, okay? Two, you have to think about that part of the theorem that a derivative and an integral actually undo each other, okay? So if for like where is h prime equal to something, then I could look at the value of the graph. Like let's do one more, or just to show you something here. So let's say h prime of no, can't do that. So if I wanted like h prime of 4, remember the derivative of h gives you, so the first derivative of h would imply f of 4, right? And what is f of 4? 0, yeah. So the answer would be 0 for that one. Okay? So that, like, these two kind of are doing kind of the same thing. And then there's these ones up here where you have to really think about the formula, the fact that it starts from 1 to x, and we're talking area as we go. So it's kind of a different way of analyzing a graph from what we've done in the past. About this antiderivative area type stuff. Deal with it. Okay. So at least one like that in your homework. And once we get to our review for your test, we'll go back and revisit some of these again, just to make sure you guys have that type of understanding under wraps pretty well. So I'll let you guys get to work, and just let me know if you got any questions.